Architectural patterns are high-level design strategies that define the overall structure and behavior of an application. While design patterns deal with smaller, reusable solutions within code, architectural patterns shape the entire app's layout, communication flow, scalability, and responsibilities. In the world of modern JavaScript frameworks, architectural patterns are the backbone of how applications are organized, developed, and maintained, especially as apps grow in size and complexity. In React, for instance, one of the most dominant architectural approaches is component-based architecture. This pattern breaks down the user interface into small, self-contained, and reusable pieces called components. These components manage their own state or accept data via props, and together they form a cohesive UI. This approach encourages thinking of the interface as a tree of building blocks, where components can be nested, composed, and reused. It's common to layer these components hierarchically, separating presentation components, also called DOM components, from container components or smart components. The presentation components are focused on rendering and styling, while containers manage logic, data fetching, and state. React also supports an architecture influenced by unidirectional data flow, where data moves in a single direction from parent to child. This is reinforced by state management tools like Redux or ZooStand, which implement variations of the Flux architecture. Flux emphasizes a centralized store and clear flow. User actions are dispatched, reducers update state, and components re-render in response. This pattern is especially effective in complex applications where managing state across many components becomes challenging. Angular takes a more opinionated architectural approach. It uses a layered architecture with clear separation of concerns. Components handle presentation, services handle logic, and modules group related functionalities. Angular is deeply rooted in the Model View Controller, MVC, and Model View View Model, MVVM, paradigms, depending on how developers interpret it. The framework's use of dependency injection is key to enforcing decoupling and testability. Components act as the view layer, while services act as the model and controller logic. Observables, via RxJS, integrate tightly into this architecture, allowing reactive programming and stream-based communication across parts of the app. Node.js applications typically follow a modular architecture, where the application is broken into distinct modules that each handle a specific concern, such as routing, database access, authentication, or business logic. Because Node is a back-end runtime, it often leans on architectures like layered architecture or hexagonal, ports and adapters, architecture. In Express.js, the classic layered approach is very common. Requests come into the router layer, pass through middleware, hit controller functions, and finally touch service and data access layers. This separation promotes maintainability and makes it easier to replace or test individual layers. Nest.js, built on top of Node.js and inspired by Angular, enforces a highly structured, layered architecture. It embraces concepts like modularization, dependency injection, and decorators. Nest promotes domain-driven design, DDD, and the command query responsibility segregation, CQRS, pattern. In DDD-style apps, the business domain is central, and application logic is built around it using entities, value objects, and services. CQRS further separates read and write operations, allowing better performance optimization and scaling, especially useful in microservice or event-driven architectures. Next.js, which extends React, blends front-end and back-end logic using a hybrid architecture. It supports both client-side and server-side rendering, enabling developers to decide per page whether data should be fetched on the server, at request time, or during build time. This introduces an architectural model called the isomorphic architecture, where the same JavaScript code runs both on the client and the server. This dual execution capability requires careful planning around data fetching, caching, and user experience. Additionally, micro front-end architecture is gaining popularity in large-scale JavaScript apps, especially those built with React or Angular. This approach breaks down a large front-end into smaller, independently deployable applications that work together as one. Each micro front-end may be built by a separate team, using different stacks if needed, and then integrated into a shared shell or layout system. Module Federation in Webpack 5 has made this much more feasible in modern ecosystems. At the core of all these frameworks is a shared goal: to make code more maintainable, scalable, and testable by applying architectural principles suited to their context. Whether it's unidirectional data flow in React, layered service architecture in Nest.js, or reactive pipelines in Angular, each framework builds on a set of architectural patterns that guide how applications are structured. Architectural patterns are the foundational blueprints behind how software systems are structured. They define how different layers of an application interact, how responsibilities are separated, and how data flows throughout the system. These patterns aren't tied to any specific language or framework, but in modern JavaScript development, many of them are adapted and customized to fit the needs of web and server applications. Let's explore some of the most widely recognized architectural patterns and how they are understood and applied. One of the most classic and enduring patterns is Model View Controller, or MVC. It divides an application into three core components. The model represents the data and business logic, the view is the user interface, and the controller handles input, transforming it into actions on the model or view. This separation allows developers to work on different parts of the application simultaneously and promotes better code organization. In traditional web applications, especially those built with frameworks like Express on Node.js, MVC remains a common way to separate concerns. The router often plays the role of the controller, while models, such as Mongoose schemas, manage data, and templating engines or front-end frameworks handle the view. A variation of MVC that gained popularity, especially in front-end frameworks like Angular, is Model View Model, or MVVM. In this architecture, the view model serves as a mediator between the model and the view. It exposes data and commands to the view while maintaining logic and state. What makes MVVM distinct is its reliance on data binding, automatically synchronizing the state between the view and the view model. This pattern is deeply embedded in Angular's reactive design. With tools like RxJS, the view model, or component class, reacts to changes in observables and updates the view seamlessly, without the view needing to directly handle business logic. Model View Presenter, or MVP, is another derivative that emphasizes testability and control. The presenter acts similarly to the controller but holds more logic and is responsible for updating the view explicitly. The view becomes passive, relying on the presenter to tell it what to display. This pattern was historically popular in desktop GUIs and has been adapted in scenarios where decoupling the view from logic is especially important. For example, in large-scale React applications using custom hooks or class components. Moving beyond UI-centric architectures, modern applications often adopt patterns focused on data management and service orchestration. One of the most important of these is Command Query Responsibility Segregation, or CQRS. This pattern separates operations that change data, commands, from those that read data, queries. By splitting reads and writes into different models, developers can optimize each side independently. In JavaScript, CQRS is increasingly used in back-end systems, especially those built with Nest.js, which provides decorators and modules that align naturally with command and query segregation. It's particularly valuable in event-driven or microservice systems where write operations might trigger workflows or events, and reads may be handled by read-optimized databases or caches. Another powerful and growing architectural concept is event-driven architecture. In this model, components of the system communicate via events rather than direct calls. When an action occurs, it emits an event, and other parts of the system can react to it asynchronously. JavaScript, with its asynchronous nature and the widespread use of Node.js, is a natural environment for event-driven design. Systems using tools like Kafka, RabbitMQ, or even basic Node.js event emitter objects are embracing this architecture to build decoupled and reactive systems. Closely related is microservices architecture, where an application is composed of small, independent services that communicate over HTTP or messaging protocols. Each service handles a specific domain or function. In JavaScript development, this often manifests as multiple Express or Nest.js services running independently, orchestrated through APIs or message queues. This approach allows for better scalability and team autonomy but introduces complexity in communication, consistency, and deployment. On the front end, there is increasing interest in micro-front-end architecture. Similar to microservices, this pattern breaks the front end into smaller, independently deployable pieces. In modern React or Angular ecosystems, micro-front-ends allow teams to build, test, and deploy UI features separately. Tools like Webpack's Module Federation and frameworks like Single SPA help implement this pattern in practice. Another timeless pattern is layered architecture, where software is organized into layers such as presentation, business logic, and data access. Each layer has a defined responsibility and interacts with adjacent layers. This is one of the most common patterns in web applications. In a Node.js or Nest.js project, you typically see this reflected in separate files or modules for controllers, presentation, services, business logic, and repositories, data access. This structure keeps concerns cleanly separated and makes testing and maintenance easier. Hexagonal architecture, also known as ports and adapters, is another elegant pattern that's gaining traction, especially among developers looking for clean architecture principles. In this model, the core application logic is kept independent of external systems like databases, web frameworks, or APIs. Communication happens through defined ports, interfaces, and adapters implement those ports. This allows the application to be more testable and framework agnostic. It's a powerful concept in TypeScript-based Nest.js applications, where interfaces and dependency injection can enforce strict separation between core logic and infrastructure. Finally, clean architecture, championed by Robert C. Martin, Uncle Bob, builds on ideas from hexagonal and layered architectures. It emphasizes boundaries, where the innermost layers contain pure business rules, and outer layers handle delivery mechanisms like HTTP or UI. Dependencies only flow inward. In JavaScript applications, this often involves careful layering of use cases, services, interfaces, and controllers, especially in back-end applications where maintainability and testability are paramount. All these architectural patterns are not mutually exclusive. In fact, many real-world applications blend multiple patterns. A React app may use component-based architecture with Flux-style dataflow. A Nest.js backend may combine layered architecture with CQRS and hexagonal boundaries. The goal of any architectural pattern is not to be academically correct but to provide structure, scalability, and clarity to a growing codebase. System design is the art and science of shaping large-scale software systems that are scalable, maintainable, and reliable. At its heart, system design is about breaking down complex problems into organized components that work seamlessly together. It encompasses architectural decisions, infrastructure planning, and communication strategies between services. When building systems like Facebook, Twitter, Netflix, or Amazon, engineers must think far beyond the code. They need to design systems that can handle millions, even billions, of users across the globe, all in real time. The first thing that becomes apparent in designing these kinds of systems is the need for high availability. A highly available system is one that keeps running, even when parts of it fail. Users don't tolerate downtime, especially not at scale. To achieve this, companies rely heavily on redundancy. Instead of having one server or database, they replicate data and services across multiple machines, data centers, and even continents. This way, if one region goes down, traffic can be rerouted to another without service disruption. To distribute that traffic globally and efficiently, systems use load balancers. Load balancers sit at the front of a system and distribute incoming requests to different back-end servers based on availability, health, or even geography. For a platform like Facebook, which serves content in milliseconds to billions of users, load balancing is critical not only for performance but also for failover. Facebook, for example, has data centers around the world and uses intelligent routing to send users to the closest, fastest, and healthiest servers available. Caching is another fundamental building block in high-scale system design. Systems like Instagram and YouTube rely heavily on caches to serve frequent data quickly, whether it's a profile page, image, or video metadata. Caches sit in front of databases and store frequently accessed information so that repeated requests don't hammer the database. This dramatically reduces latency and system load. Facebook employs multiple layers of caching, including in-memory caches like mumcached and geographically distributed edge caches through CDNs, content delivery networks, to serve static content instantly to users no matter where they are. At the core of any large system is its data storage strategy. Relational databases, while still useful, often struggle with the massive volume and velocity of user data in a global platform. That's why modern architectures increasingly embrace distributed databases like Cassandra, DynamoDB, or Bigtable. These databases spread data across many machines and use replication and partitioning, sharding, to scale horizontally. This allows platforms like WhatsApp or Twitter to write and read enormous amounts of data reliably and with low latency. Designing for consistency and availability becomes a balancing act in these environments. According to the CAP theorem, a distributed system can only guarantee two of the following three: consistency, availability, and partition tolerance. Systems like banking apps often prioritize consistency, ensuring every transaction is accurate, whereas social networks like Facebook may choose eventual consistency for better availability and user experience. For example, if you like a post and it doesn't immediately reflect on another user's screen, that's acceptable as long as the system converges eventually. In modern system design, microservices have become the preferred architectural style. Instead of a monolithic application handling everything, large systems break functionality into independent services, authentication, payments, messaging, content delivery, each deployed and scaled separately. This allows teams to iterate quickly, isolate faults, and scale parts of the system as needed. Companies like Netflix have famously adopted microservices, with hundreds of services working together to stream movies reliably to millions of users. To glue all these services together, message queues and event buses play a vital role. Instead of having services call each other directly, systems often rely on asynchronous communication using queues like Kafka, RabbitMQ, or SQS. When a user uploads a photo on Facebook, for instance, that event can be published to a queue. Different services, like resizing, tagging, or analytics, can then consume and process the photo independently. This decouples services and makes the system more fault-tolerant and responsive. To monitor and keep these complex systems running, companies build robust observability and monitoring stacks. They log every action, track every metric, and alert engineers to anomalies. Netflix, for example, collects real-time telemetry across their entire system and uses chaos engineering practices, intentionally breaking things, to ensure their systems can handle failure gracefully. Finally, the importance of security and privacy cannot be overstated in large system design. Authentication, authorization, rate limiting, encryption, and data governance must be baked into every layer. Companies like Google and Amazon design their systems with zero-trust models, where no internal component is implicitly trusted, and all access is verified continuously. In designing systems like Facebook, Twitter, or Slack, what ultimately makes them successful is not just clever algorithms or powerful hardware, but thoughtful architecture. These companies blend distributed systems theory with real-world engineering to build platforms that feel instantaneous and reliable to the user, despite the enormous complexity under the hood. Designing a video platform, from something small like a course site to something massive like YouTube, involves deep consideration of storage, compute, scalability, resilience, and data modeling. You're not just dealing with metadata, titles, descriptions, likes, but also with huge binary files, videos, heavy I/O, and user engagement at scale. Let's walk through the system design of a video platform with a focus on memory, storage, replication, and database selection. Understanding storage and memory requirements. When it comes to video, storage is king. Unlike text or image-heavy platforms, video platforms consume enormous amounts of disk space and bandwidth. To calculate the necessary storage, start by estimating the average size of a video upload, the number of uploads per day, the retention policy, how long to store them, the number of transcoded formats, resolutions, bitrates. Say you expect users to upload 10,000 videos per day, and each video averages 200 megabytes, a few minutes at 720p. That's 2 terabytes per day. If you offer multiple formats, 240p, 480p, 1080p, your storage may triple, becoming 6 terabytes/day. Over 30 days, you need 180 terabytes, just for raw video content. For memory, RAM, this mainly impacts real-time processing components, transcoding services, queues, API gateways, etc., rather than raw storage. Your memory needs will depend on the number of concurrent video processing jobs, the chunk size processed in memory, and the I/O handling efficiency of your services. Memory-bound services like transcoders, MPEG pipelines, should run on compute-optimized instances with high RAM and possibly GPU acceleration. Where and how to store videos. You don't store large video blobs in a traditional database. Instead, you use object storage systems. Amazon S3, or Glacier for archival Google Cloud Storage, Azure Blob Storage, or even self-hosted MinIO or Ceph for on-prem solutions. These systems are designed for high durability, often 99.99999999999%, and scalability. Video files are stored as blobs, and only metadata, title, description, user ID, views, etc., is stored in a database. To reduce latency globally, video platforms use CDNs, content delivery networks, like Cloudflare, Akamai, or CloudFront. These replicate and cache popular video content closer to users, reducing load times and reducing bandwidth usage from your storage buckets. Replication strategy. Video platforms need high availability and fault tolerance, especially for critical metadata and user actions. For storage, use geo-redundant object storage to replicate videos across multiple regions. Implement multi-zone replication for durability. For metadata databases, replication ensures read scalability and resilience. Use primary replica, master-slave, or multi-primary setups. Choose the number of replicas based on read load, for example, search, home feed disaster recovery requirements. Regional access patterns, APAC versus EU versus US. A typical rule of thumb is 3 to 5 replicas, with at least one in a different region if you want disaster tolerance. Database selection, metadata and indexing. For the structured part of your system, metadata, users, video indexing, comments, you need a robust database. The choice depends on the scale, relationships, and expected query patterns. For early-stage platforms, PostgreSQL or MySQL are great. They support relational data and full-text search. For higher scalability, consider CockroachDB for horizontal scaling of relational data, or Google Spanner. For massive, distributed metadata, Cassandra or ScyllaDB are popular in video and messaging platforms. They scale horizontally and offer high write throughput. If you need fast search and filtering, for example, video title, tags, transcripts, integrate Elasticsearch or OpenSearch as a secondary store. User-generated content, comments, likes, subscriptions. For user interactions, relational databases work fine early on, but eventually, you'll hit read/write bottlenecks. Here's what many platforms do. Store likes/views in Redis, fast, volatile, periodically write to the main database. Use pub/subsystems like Kafka for event handling. For example, user-liked video, new comment. Use graph databases like Neo4j for social relationships, who follows whom, recommendations. Scalability and traffic handling. Your backend needs to be event-driven and horizontally scalable. Break the monolith. The video upload service should chunk, validate, and in-queue jobs. A transcoding microservice consumes from the queue and processes video. MPIG-based a metadata service tracks upload status, format availability. A streaming service handles signed URLs and user playback requests. Services communicate via APIs or message queues. Use RabbitMQ, Kafka, or Google Pub/Sub for high-throughput messaging. Analytics and view counts. You can't afford to write every video view to your main database. It's too slow and expensive. Instead, collect views as event streams. Kafka or Redis streams process them in batches or via streaming engines like Apache Flink or Spark Streaming. Aggregate into time series databases like InfluxDB or long-term warehouses like BigQuery or Redshift. Security, upload control, and delivery. Protect video uploads using signed URLs. Let users upload directly to S3 via pre-signed URLs, not your servers. Scan for malware and enforce content policy using serverless functions or moderation services. For delivery, make video URLs expirable and signed to prevent hotlinking. Apply rate limiting per IP/user to protect against abuse. Final notes. A day in the life of a video. When a user uploads a video, it's first sent to an object store. A job is queued to transcode it into multiple resolutions. The processed videos are stored back in object storage and marked as ready. The metadata is indexed and searchable. The video is then served via CDN, and interactions like views and likes are collected as event streams for analytics and personalization. Designing this kind of system means balancing user experience, fast video start times, responsive UI, with infrastructure efficiency, minimized costs, optimal resource use, and long-term scalability.